Hi everyone, this is Manel Smine. In this work, I am going to tell you about my paper titled A Priority-Based Domain Type Enforcement for Exception Management. This is a joint work with David Espès from University of Western Brittany, Nora and Frédéric from Polytechnique Montréal, and Marc-Oliver from IMT Atlantique. The plan of my presentation is as following. I will start by presenting the context and the problem addressed by this work. Then I will give you an overview of the related work. In a third part, I will present our contribution, which will be followed by some experimental results. And I will conclude my talk and give some future work. So let's start by the context. In the literature, access control policies can be classified in three categories: open, closed, and mixed access control policy. The open access control policy contains only negative authorizations. It is used only in scenarios where the security need is not strong. The closed access control policy contains only positive authorizations. This type of policies is used in most systems as it ensures the least privileged access principle. And finally, the mixed access control policy includes both positive and negative authorizations. This kind of mixed policy is often used to specify high-level specification of complex security policies. While the mixed policies are usually used to specify the high-level access control requirements, the deployment relies generally on closed policies. As a result, mixed policies need always to be transformed to closed policies. This transformation looks like a straightforward operation. However, as we will see later in this presentation, transforming mixed policy towards closed policy can be challenging, especially when the latter contains exceptions. Exceptions are often used in mixed policies. An exception can be used to grant access only to a specific user. For example, a security administrator can use an exception to grant access to the database server only for Bob. The exception can also be used to revoke prohibitions. For example, the security administrator can use an exception to prevent only Bob from accessing the database server. As we will see later on this presentation, existing methods used to transform exceptions towards a closed policy increase considerably the number of low-level rules to be deployed, which leads to quite complex closed policies and makes their management difficult for security administrators. As use case, we consider the management of access control in network function virtualization services. Network function virtualization was proposed to improve the flexibility of network service and to allow a better information sharing between their components. In one side, most existing policy specification model of NFV services are using high-level mixed policies. In the other side, most promising access control models on NFV services are based on domain type enforcement DTE to allow both access and flow control management. Actually, existing DTE models are based on closed policies. So, the questions we want to answer in this work is how to deploy efficiently high-level complex mixed policies using a DTE-based model. Few access control policies management on network function virtualization have been proposed in the literature. The most interesting approaches have been proposed this year by Suarez et al. And Smine et al. Suarez et al. Proposed an approach that combines the best of RBAC and DTU to allow secure resource sharing among the different players involved in providing services over 5G networks. Smine et al. Proposed an access control as a service model for NFV services that can handle most kinds of access control policy models and provides an efficient method for deploying access control policies at the concrete level without requiring the modification of the NFV infrastructure. Unfortunately, for both approaches, the deployment of complex policies containing exceptions leads often to very complex DTO specification. Let's move now to the third part in which I will present our contribution. Let's start by the exception formalization. Given a rule R1 that states that the subjects in S1 should be allowed to perform the actions in A1 on the objects in O1, and a rule R2 stating that the subjects in S2 should not be allowed to perform the actions in A2 on the objects in O2. Formally, R1 and R2 form an exception if and only if the intersection of the set of subjects S1 and S2 is not empty, the intersection of the set of actions A1 and A2 is not empty, the intersection of the set of objects O1 and O2 is not empty, and that R1 and R2 have different decisions. The exception can be transformed trivially towards a closed policy according to the following two cases. If the positive authorization R1 is enforced before the negative authorization R2, the transformation is achieved by removing the negative authorization. However, if the negative authorization R2 is enforced before the positive authorization R1, then the rules R1 and R2 should be rewritten to three positive authorization R star 1, R star 2, and R star 3. We formally proved that in the worst case, A1 different from A2, O1 different from O2, S1 different from S2, each exception will be rewritten in three positive authorization rules. So, for each transformation of an exception, new positive authorization rules are added to the closed policy. Things get more complex if more negative authorization, the case of the rule 3, are in exception with the new added positive authorizations R star 1, R star 2, and R star 3. This means that we have three more exceptions to transform. Each one will add more rule to the closed policy. We evaluate the asymptotic complexity of the previous transformation method in terms of number of rules in the closed policy. We proved that in the worst case, the number of rules in the closed policy grows exponentially as a function of the number of exceptions in the policy. For those who are interested, you can find the proof in the paper. Closed policy can be straightforwardly deployed in a DTO-based access control system by considering each subject of a rule as a DTO domain and each object as a DTO type. Hence, the number of DTO type and domains will also grow exponentially in the number of exceptions in the policy to be deployed. This will, on one side, increase the time needed for policy evaluation during access evaluation, which may impact the efficiency of the system over which the policy is deployed. In addition, as we mentioned before, this makes difficult for security administrators to understand, read, update, and maintain the deployed DTO specification. Let us move forward to see how we manage to overcome these problems. The classic DTO model is based on three key concepts. First, domains, which are used to group a set of subjects according to specific properties. Second, types that are associated to a set of objects. The association between a domain and type define a set of actions that are allowed to be performed by the subjects of the domain on the objects associated to the type. Third, domain transition, allowing a subject to transit from a domain to another. We extend the concept of DTO transition by adding a transition condition describing a set of requirements that should be fulfilled by an entity to be able to transit. Then we add the concept of priority to a domain transition. A priority is a numeric value that will be associated to a domain transition. In case in which several transitions are possible for an entity, it will help the system deciding which domain transition should be performed by the entities. The prioritized transition is the one that has the highest priority. For example, the subjects in D1 can transit to D2 if and only if the priority P1 is higher than P2, and can transit to D3 if and only if the priority P2 is higher than P1. So let us see how we used the transition conditions and priority to solve the tackled problems. So let's consider two rules, R1 and R2, that form an exception. The rule R1 is saying that any entity having the subject S1 cannot perform the actions A1 on any entity having the object O1, while the rule R2 ensures that any entity having the subject S2 can perform the actions A2 on any entity having the object O2. So, to transform this exception, we start by creating a DTO domain S1D that we are going to associate to all the entities characterized by the subject S1, and we create a DTO type O1T that we associate to all objects that are characterized by O1. We do the same thing for the rule R2, so we create the DTO domain S2D that we are going to associate to all the entities characterized by the subject S2, and a DTU type O2T that we associate to all objects that are characterized by O2. We then create a DTO domain O1D and a domain transition between S1D and O1D, knowing that the domain transition is enabled only if the subject that is going to transit wants to perform the action A1 on an object having the type O1. We create also a DTU domain O2D and a domain transition between S2D and O2D, and we authorize all entities in O2D to perform the action A2 on all entities having the type O2. And finally, we associate two priorities P1 and P2 to the transitions between S1D, O1D, and S2D, O2D, such that the value of the priority P1 is greater than the value of P2. Let's now see how access queries are evaluated using our extended DTO model. So let's consider the following access query AQ1 that informally says that the subject is in S1 wants to perform the action A1 on the object O1. Initially, the access query AQ1 belongs to the domain of its subject, hence it will be in the domain S1D. AQ1 satisfies the conditions of the domain transition T1, therefore it will transit to the domain O1D, or the domain O1D does not have any permission on the object of O1T. As a result, the access requested by AQ1 will be denied, which is conform to the initial policy. Let's consider a second access query AQ2 that requests the application of an action in A2 by a subject belonging to S2 on an object associated with the type O2. Initially, AQ2 will belong to the domain S2D. As you can see, subjects in S2D cannot directly perform actions on O2T, and the only possible domain that can be accessible to AQ is the domain O2D. So, the access query will transit to that domain from which the subject can perform the requested action of any object associated with the type O2T. As a result, the access requested by AQ2 will be granted, which again is conform to the initial policy. Let's now consider a third access query, AQ3, that informally says that a subject in the intersection of S1 and S2 wants to perform an action belonging to A1 and A2 on an object associated to both the types O1T and O2T. So the access query starts from the intersection of the two domains S1D and S2D. Again, the subjects in the intersection of S1D and S2D cannot directly perform actions on objects associated to O1T and O2T. So the two domain transitions T1 and T2 are possible. However, the access query will be forced to transit to O1D since the transition T1 has higher priority than the transition T2. As a result, the access query AQ3 will be denied, which again is conform to the initial policy. In contrast to classical exception management in DTO models, our proposed transformation method does not require a large number of new rules, domains, and types. The correctness of the exception deployment method in our extended DTO model has been proved in the paper. Alright, let's see now some experimental results. So, we aim to compare the performance of our proposed model with the classic DTO-based access control model for NFV services. The figure at the left compares the growth of the number of required DTO domains and types in classic and priority-based DTO as a function of the number of exceptions in the policy. The blue and orange color represent respectively the growth of the number of required DTO types and domains in classic DTO. The green and the red color represent respectively the growth of the number of required DTO types and domains in priority-based DTO. As you can see, when the number of exceptions grows by a factor of 6, the number of DTO domains and types grows by a factor of 2 for the priority-based DTO, while growing by a factor of 192 in the case of classic DTO. The figure on the right compares the number of rules in the classic DTO specification and in the priority-based DTO specification as a function of the number of rules in the policy to be deployed. When the latter increases from 10 to 60, the number of rules in the priority-based DTO increases also by a factor of 6, while the number of rules required by the classic DTO grows by a factor of 230. In addition, we evaluated the transformation required time and the access query evaluation time. The figure at the left compares the time required for transforming a high-level policy towards a classic DTO and priority-based DTO specification. In the case of priority-based DTO, the time of transformation is almost constant while growing by a factor of 10 exponent 5 in the case of classic DTO, as the number of exceptions increases by only a factor of 10. The figure at the right compares the time needed by both classic DTO model and our priority-based DTO model for the evaluation of an access query. Our model drastically reduces the time needed for evaluating an access query as the number of exceptions in the policy to be deployed increases. This is due to the fact that in the classic DTO specification, the number of domains and types to be matched with an access query grows exponentially relatively to the number of exceptions. We also compare the round-trip time of a network request when using the classic DTO model and our extended DTO model as a function of the number of exceptions in the enforced policy. As you can see in the left side figure, when the classic DTO model is used, the RTT increases by a factor of 210, while increasing by only a factor of 4 when our priority-based DTO model is used, as you can see in the right side figure. This is mainly due to the time required to evaluate access queries with both solutions. This brings me to the conclusion of this talk. I would like to conclude this talk by saying that we defined a probably correct DTU-based access control model, allowing an efficient deployment of complex access control policies that contain exceptions and conflict rules on NFV services. The conducted experiments show that our proposed model is by far more efficient than the existing solution when dealing with high-level complex policies containing exceptions. As future work, we want to explore how to use our extended DTU model to optimally deploy access control policy on NFV services. Thank you for watching.